Today we have Alex and Marcus from the American Chemical Society in California. And without further ado, we'll transfer the program over to them.
Great, thanks, Dennis. And yeah, thank you, North Bay Science Discovery Day, and the host and everybody for attending this morning. So I'm just going to start by sharing my screen and sharing a couple of slides with you before we kind of get into more of the hands-on aspect of today's presentation. Sharing, and I know no one can actually speak directly to me, but if Dennis or Alex could tell me that my screen's sharing properly, that'd be great. Okay, we're good. Okay, so today the title of our presentation is Sustainable Polymers and Reducing Our Footprint with Chemistry, presented by myself, Dr. Marcus Cole, and Dr. Alex Madonik. And so I'll just give you guys a little background about me and my background when it comes to polymers. So I got my bachelor's degree back in 2014 from the University of South Carolina. I actually wasn't originally a chemistry major. I actually worked for the Daily Gamecock, our college newspaper, for a year or so before transitioning into chemistry. So I spent a lot of time in Williams-Brice Stadium watching football games. But then when I wasn't there, I was running reactions in Brian Benzowitz's chemistry lab, where I really got my exposure to polymer chemistry. Here's a pretty cool image of my undergraduate project where we made these magnetic nanoparticles that had these polymer brushes coming off of them that actually carried penicillin. And so we used them as this recyclable drug delivery system, really using polymers to have a more sustainable solution to treating bacteria. And after spending some time doing that, I went and got my master's degree and PhD from the University of Massachusetts in Amherst, where I got to really learn a lot about polymers, both their chemistry, physics, as well as their engineering, as well as learning about kind of talking to students and doing things like this and educating people on polymers, as well as my actual thesis work, which focused on taking polymers and putting them into solar cells to improve their performance. So a lot of my background has been in sustainability as well as in polymer chemistry. And for the last couple of years since finishing school, I've had 2 different jobs. I first started at the Clorox company where I was at for most of the pandemic, working on our wipes products, but really looking at ways to bring more sustainable raw materials into our wipes products, as well as bring out new properties that the consumer might like, better hand feel, better smell, and even better cleaning performance. And in my current role, I work at a company called E-Ink that actually makes these low-powered displays that actually can create an image without applying any additional voltage. So it's a fairly low-power energy display, which is then, again, contributing to sustainability. And so on that team, I get to design new molecules and include them into our display technology and try to improve the performance of our devices. And so that's a little bit about me. And so, but I thought I'd like to get us started with kind of talking about the building blocks that we're going to be using today when we're talking about polymers. So the periodic table of elements actually contains a lot of atoms or elements, but we're really only interested in about 4 of them. So we're going to be thinking about hydrogen, oxygen, nitrogen, and carbon. These are the ones that we really use a lot in organic chemistry, which is kind of fundamentals behind polymer chemistry. And for all the purposes of this session or just moving forward, for most of the time, hydrogens are going to normally make a single bond, oxygens will normally make 2, nitrogens will tend to make 3, and carbons tend to make 4. And if we take all of these atoms and start to combine them into different structures, we can get things like molecules that have a lot of interesting properties. We have things like ethylene, which is a gas that actually contributes to the ripening of fruit. We have glucose, that is actually a component to sucrose that comprises all of our sugar products that we normally use, as well as amino acids that are actually used in the preparation of artificial sweeteners that are lower in calorie count, but also still kind of have that same sweet taste that we like. And so if we take these molecules that already have interesting properties and link them together, and not just a few of them together, we're talking about tens of little molecules stringed together, up to millions of molecules stringed together in these really long chains that essentially look like spaghetti. we get things like polymers, aka our macro molecules. These are big guys. So when you go from ethylene to polyethylene, you go from a gas that ripens fruit to now a solid material that can be blow molded or extruded to form different kinds of pieces, or even into thin film that forms our traditional plastic bag. With cellulose, which is the polymer of glucose, we actually end up getting wood, which goes into a lot of different other products, as well as polymers of amino acids can form a lot of different things, but one of the ones that you're probably most familiar with is wool. And so polymers really are these interesting molecules that come from smaller molecules. We kind of link them all together to make these longer chains, and then we get these more unique materials that have a lot of different kinds of properties. And so when we think about synthetic polymers, probably the ones that you're most familiar with have these recycling symbols around them, moving from 1 to 6. And so at the top, you have things like PET, which is fairly easy to recycle, which is why it's denoted with the 1 symbol, all the way down to polystyrene, which is denoted with the number 6, which is probably the most difficult to recycle. Either it's the most costly or the most energy intensive. But beyond some of these, I guess, traditional polymers, there's actually a lot of interesting things that you can do with these materials, whether it's using them to make photoresist to actually design microelectronics. This is how we make our microchips, is using a little polymer layer that allows us to pattern the circuit onto the wafer. We can also use them as the active layer component in things like a flexible LED phone screen, or we can even do really big things with these polymers and use them as a matrix and a composite material so that we can print pieces of things like airplanes. So this Boeing 787 Dreamliner is actually predominantly a polymer composite. So it's a big plastic that's just got some additives in there that can improve its strength, but it's ultra light, ultra fast, and has a lot of the desirable properties that you want out of an organic material, but still with some of that strength that you need from an inorganic material like metal.
Hey, Marcus, somebody asked, what age did you get involved? Did you get interested in chemistry and polymers?
Sure. Yeah, I got interested in polymers when I was like 19. So I feel like a lot of other people that are in the sciences probably knew they wanted to do this from day one. I really didn't like chemistry as a high school and middle school student. I actually got a C in chemistry when I was in high school, and now I have a PhD. So you can kind of figure out your way into a field if you really have an interest in it. Yeah, thanks for the question. Yeah, and so the last little slide before we kind of get into the experiment that I have laid out in front of me is about polymers that can go into the body. And so it's really interesting the things that we can do with polymer chemistry. We can design materials that can be stable as well as strong enough to go in the body to form hip replacements. We can create materials that can actually form a coating that goes over your tooth after you have some decay removed, and it can replace metal fillings with these polymer fillings that easily get cured under some UV light. So if you ever go to the dentist and they squirt something in your mouth that kind of smells like paint and they hit it with a light, it's just a UV curable resin that's totally safe to go into your mouth, but it is essentially bio paint. It's the same chemistry fundamentals that go into making the kinds of paints that go on your house or your car, but just applied into a more biological setting. We can also use polymers to deliver drugs, make contact lenses, as well as some biodegradable sutures. But for now, I'm going to stop sharing my screen so I can show you a little experiment that I have in front of me. So I've got 3 different cups. So one is actually my control. This has regular clear Elmer's glue that you can get from the store, as well as 2 other cups that actually I added a little bit of an additive because we're doing an experiment. So we want to have our control to see what should traditionally happen in this system. And then we're going to have our 2 different variables to compare to the control and see if anything changes. And then to the right here, I actually have a solution of borax in water. So borax is just a detergent booster. But if anybody is familiar with this kind of experiment, this is your classic slime experiment. So we're going to take some borax here and add about a tablespoon to each of our cups. And we're going to see exactly what happens. So if I take my control, swirling it around, seeing a little bit of buildup in viscosity, and at this point, I no longer have regular glue. I've got this very slimy, gooey system that has clearly changed since me adding that borax solution. In our cup A, stirring, picking up a little bit. Similar, still got the goo, looks pretty gel-like. Maybe a little wetter than the previous one, maybe seeing a little bit more dripping down. And then we have B, swirling, sticking. Still jelly, but clearly not as strong as the first one. This guy is pretty much completely solidified. There's not a whole lot of dripping going on. And so if I go back to my screen really quick, I can briefly show you kind of what was going on here. So what I essentially did was take our regular Elmer's glue, which is actually a polymer. It's actually polyvinyl alcohol, and it's got these OH groups that hang off the side of that long polymer chain that forms the backbone. And borax is actually just borate, it's sodium borate. It's just a salt that also has these hydroxyl groups hanging off the side. And when I mix the two, I actually do something that's called cross-linking in polymer chemistry, meaning I've taken one or more polymer chains and linked them together to basically form this network that takes what is normally a viscous solution like glue and turns it into a solid gel. But what I did with this other cup is I actually added in a third reagent, which is a classic alternative sweetener. It's actually called erythritol, and it also has these little hydroxyl groups in it. So what the erythritol essentially does is it competes with the polyvinyl alcohol for the borate ions, meaning that not as much of those borate ions can form that cross-linked network. So we'll go from something where we have no erythritol, that's pretty solid, to something with a lot of erythritol that still has a certain level of elasticity to it, but it still flows. This is not the same solid gel that we were working with previously. And so this is a nice little experiment that you can do at home. You can take PVOH or Elmer's glue, mix it with some borate, and add different kinds of sugars or salts that you have in your kitchen to kind of see how your gel changes. And with that, I'll kick it over to Alex, and I'd love to answer any questions that anybody has as we go through the presentation.
Okay, that was terrific. You can see my background, which is advertising an event we're going to be doing in April. We'll be back online on April 24th. And I had put into the chat the link to our website. I'll put it in again. So you can see what we're up to at the American Chemical Society. We really miss going out in public and doing these things with you. So we're doing them online. And that's what we'll be doing on April 24th as well, when in previous years, we'd be out in Martinez at the John Muir Historical Site celebrating Earth Day. Okay, and with that, I'm going to stop sharing my screen. I'm going to clear my background here, actually, and so you can see what I'm doing in the lab. Sorry, I just put the wrong thing. Because like Marcus, I want to do a little chemistry. Yeah. All right, so now you see my office. This is also my lab right now. And what I want to talk about is another wrinkle on polymers, on the same polymer we were just looking at. But before I do that, let me just say that there's a question about whether we can really recycle plastic, right? And in fact, I was just looking at an article today that was published in the online Grist newsletter about recycling different types of plastic, especially polyester, plastic number 1. And maybe they can do a better job with microwaves. That's one thing they're trying. But still, there's too much plastic in the world, right? And it doesn't go away. That's really the problem. It piles up. So what we really need is plastic that doesn't last forever, that's like paper that can be composted if it isn't recycled, right? So here's a plastic bag that's made partly out of starch. And if I throw this into a compost heap, it will turn back into soil. It will compost, okay? Now, I wouldn't put this in my own compost heap, but a city compost heap gets a little hotter. And they have a process where they can shred this thing and it turns back into compost, all right? So this will not get into the ocean and it will not stick around forever. That's the hope, anyhow.
We do have one question, and I don't know whether it's to Marcus or Alex, is what polymer experiment got you hooked on this whole, on your whole polymer interest?
What do you say, Marcus? Yeah, Marcus.
You're muted, Marcus.
Yeah.
Oh, thank you. Oh man, that's a good question. Probably the nylon rope trick is it's one of my favorite in-person experiments. It's actually it's a Schattenbaum interfacial polymerization. So you've got a water layer, and then you've got an organic layer that contain your 2 different monomers. And the polymerization actually happens at the interface. So you can take like a stirring rod and spool up the polymer as you're running it. So you can basically generate a spool of nylon in real time. I'm also a science, or a superhero nerd. I've got a polymer that's in the form of a Superman emblem on my shirt right now. So the nylon rope trick really makes me think of Spider-Man. And so that's why it's like my favorite experiment, and it got me hooked.
And the other question, sort of similar, is what got you into polymers at all? I mean, what piqued your interest in polymers?
I guess kind of the way polymer science kind of has to interface with chemistry, physics, and engineering. Because like I really like I'm a chemist by training, and like right now I do a lot of chemistry in my job. But as a polymer scientist and chemist, I need to understand if I change a functional group through some chemical modification, what does that do with the yield strength of this material, or how is it going to affect the coating properties of this material, or is it going to change the optical properties of this material? And then also, with that physics in mind, how am I going to process it? Like, can I do this roll to roll? Does this need to be solution cast? Can I do this processing from the bulk? So I think polymers really attracted me because you get to learn a lot of different sciences about one kind of material.
Right. So what Marcus is telling us is people like him are the people that invent bags like this, right? Someone had to invent this thing. Someone had to figure out how to make it, what materials are going to be used, what it's going to cost, how long is it going to take to break down, all that kind of questions would be answered by a scientist like Marcus. That's what he does. Here's some more examples of compostable plastics. These are PLA, polylactic acid. They're cups. You can buy them in the store. And again, if you throw this in your own compost heap, probably nothing happens. But if you put it in the city compost heap, these break back down with a little more heat, a little more aggressive bacteria, and they turn into soil, into dirt, right? Because they're made out of a molecule, lactic acid, which is actually found in milk and other natural sources, and it can be broken back down to biological materials. It's not a synthetic material. Yeah, but they're durable enough to do the job. Now, if you leave these out in the sun, they will actually melt. So that can be a problem. Okay. I wanted to talk about super balls, and I'm going to share my screen now. Hopefully I find the right thing that I want to share with you. Here it is. All right, so here's a patent. Yeah, if you invent something, you want to get a US patent, right? And if you're Norman Stingley, you invented the super ball. Okay, but that was in around 1960. And then he had to figure out how to sell super balls, right? And his company wasn't interested. So he went to Whammo, the folks that make Frisbees, and they worked really hard on this. And it took them several years to figure out how to make super balls. And here's the recipe, more or less. And there's a super ball, I guess. And here's the patent. And there it is, patent number 3,241,000, whatever. And notice it's assigned to Whammo Manufacturing, but I assume Norman Stingley got paid because he's the inventor. And this became really super popular. Actually, I don't know why it took them so long to get this patent, because these were really super popular in the early 60s. I remember them. Apparently, everybody in John F. Kennedy's White House had a Super Ball, and it was just a thing. They were bouncing them all over the place. It must have been a sight. Okay. In case you're not quite sure what I'm talking about, here's an article in Wikipedia. Can you all see this? I'm sharing my screen, right? This is the article in Wikipedia about Super Balls. You can read all about it. And like Whammo made a great big one and dropped it off the roof of a building. Okay, so this was in 1965 that I guess they were shipping them. All right, so it was just before this patent was issued. My mistake. Yeah. And they were making like hundreds of thousands of these every day and selling them. Yeah, and they made a great big one and dropped it off the roof of a building, and it like smashed the car on the second or third bounce. It's just crazy. Okay, so Super Balls are actually not so different from rubber, except they bounce really good. And that means they're a little harder. And they also are a little stickier. And we can actually make a Super Ball right here, right now, using the same, almost the same materials that Marcus was showing you. So I will, maybe I'll show you a couple chemical structures while I'm at it. I'm gonna stop sharing this image, which is Wikipedia, and you can find this. And I'll just go back to the chemical structures for a second. If you'll bear with me here. Okay, now I'm not finding my picture, so oops. Gotta convince my computer that's what I want to show you next. What have I got open here?
Hey, while we're waiting, Marcus, how long have you been involved with polymers?
So it's 2021. I switched my major from journalism to marine biology to then chemistry in 2012. So I've been doing polymers for like 9 years now.
Oh, okay. How about you, Alex?
Okay, so I'm not a polymer chemist, but when I first saw the slime demonstration, I was just amazed. And it was presented by a bunch of chemists from Chevron, and they've been following us around doing great demonstrations ever since. We love them. Okay. And for some reason, I've lost track of my chemical structures. Hang on just a second here. Well, here is cellulose. I'll share that one. There it is in preview. I don't know why I was having trouble getting that up. Great. Okay, I'm going to share this. I guess I just hid it from myself. I was too clever. So when you take sugar, here's sugar. This is the simplest form of sugar. It's glucose. Everyone see that? 6 carbons and 6 oxygens and 12 hydrogens. That's what keeps us going. That's what, believe me, that's what's generating the heat that is keeping us warm, and it's helping me think. We need sugar. This is the fuel that we run on, okay? And of course, it's made by plants. But if we put some of those molecules together, we get bigger molecules, and plants are really good at that sort of thing. They can make cellulose. Here it is. It's just sugar molecules lined up. That's what my shirt is made out of, right? It's cotton. It's cellulose. It's made from sugar. And here's another kind of polymer that you can make. And I'm not sure you're seeing this. Are you seeing this? Hope you are.
We can only see the
nope,
glucose
we're still
structure.
seeing the sugar. Yeah, the glucose.
Oh, okay. Oops. I got to switch shares here then. Why is that a problem? Okay, here we go. Okay, so this is starch. Here we go. There's starch. Make that a little bigger. And that's it's sugar molecules connected together. And you know what starch looks like. It's this powder, right? And it's kind of fluffy and has some funny properties if you start playing with it. I've got a bag of starch right here. Okay. It's cornstarch. And then if you connect more of those together in a certain way, you get cellulose. You get actually cotton. Let's see if I can see that one. Here's cellulose, but that's not being shared. So I got to go back and share that. I don't know why you don't see that. Here it is. So there's cellulose. That's an even bigger polymer of sugars. It's connected up a little bit differently. but that's not important to us right now. The fact is that's what my shirt's made out of. It's cellulose, it's cotton. All right, all made from sugar. Okay, so we're gonna make a super ball, at least we're gonna try. We need a recipe, right? Because we gotta throw in something different. In fact, the magic ingredient here is gonna be starch. So I have that recipe open. And I really recommend this particular, chemist who publishes stuff online. Just great stuff. Where did my recipe go? Well, let's see. Oh, I've lost track of that. Oh, because I have it open here. Here we go. Let me open that. Too much jumping around. So I'm actually going to grab this URL and put it in the chat in case anyone wants it. Because this chemist has great stuff online and you can find all kinds of fun things to do. Here we go. But I'm going to share that, that particular page right now. Here it is, how to make a super ball, right? And notice the author here is Anne-Marie Helmenstein, and she has a super series of articles for the public, for all of you, about all kinds of chemical topics, some pretty crazy stuff. But here's super balls. Now they don't quite look like that, turns out. Here's what we're gonna do. We're gonna take borax, which Marcus just told us about. It's gonna be our cross-linker, but we're also using starch as a cross-linker in this case, and it's gonna strengthen the product, right? It's gonna make it more stiff. And then we're gonna use Elmer's glue, right? And then we need some water and maybe some food coloring. That's optional. I'm gonna skip it. And here's her procedure. Okay. And I'm going to show you what happened when I follow that procedure. All right. Okay. We're getting ready to go in the lab, right? Okay. I know I'm not really going anywhere, but if we were getting ready to go in the lab, what is the first thing we should do? Anybody know? What do you think is the first thing we should do when we go in the lab to do an experiment? Well, the
Safety.
right answer is put on your safety goggles. Okay. Now I know none of this stuff is going to hurt me, but just in case, I'm making sure you know about being safe in the lab. That's my first message. That's my first thing that I'm teaching you about going in the lab and doing work, is to be safe. And this is the first thing you do. Now today, nothing's going to happen to me. There's not going to be anything flying around, no explosions. But this protects my eyes, which I really don't want to have to lose. And you only get one chance at this. If something goes wrong in the lab and you're not wearing your safety goggles, that's it, right? I don't want to dwell on this, but I want to make it very clear, right? It's just like getting in your car. What's the first thing you do when you get in a car? You put on your seatbelt. Now, you don't need that seatbelt till you crash. I have crashed. I would not be sitting here right now. I would have died in 1980. That's 41 years ago, if I weren't wearing a seatbelt one day when I rolled my Volkswagen Bug. So I'm just saying, you only get one try at this. Put on your seatbelt and wear your goggles. Okay, we're ready to do some chemistry. And the next thing we need to do, by the way, is make notes. Now, I made notes on the recipe here. So I know what I did last time. And if you don't make notes, you think you'll remember everything, but you don't, okay? Right? And the other thing is, let's say you want to get a patent, but you don't have notes, you have no proof that you ever did the experiment, okay? I know that sounds kind of silly, but if you don't have it written down, it never happened. Okay, we're gonna make our super ball. So I'm gonna stop sharing here so you can see what I'm doing. There we go. And it's real simple. We're gonna weigh out some starch in our little container here. I'm gonna turn on my balance and put it on 0. And I'm gonna switch to grams, even though this thing likes to do ounces, right? Because I do metric. Now the recipe says a table.
Hey, Alex, just so you know, you're at 10:30, so.
Yeah, we're going to be done in about 2 minutes. All right.
Okay.
The recipe says a tablespoon of starch. There it is. And that seems to weigh 9 grams today. Last time I did this, it was 8 grams, but this balance isn't very precise. Cheap kitchen balance. There we go. Right. And the recipe also says I should dissolve the borax in water, but I found that that doesn't work too well. In fact, if you do that, what you get is kind of a slimy mess, which is fun, but it's not a super ball, right? Okay, I'm moving my chair out of the way. Here's experiment number 1, right? I did this a couple days ago. That is not a super ball. It is a blob. Okay, that didn't work so great. So we had to change the recipe a little bit. And this is science, right? You keep measuring and you keep doing the experiment different ways, and you make a notes and you see what happens. And this is what happens. What I decided to do was to add a little bit of borax as a solid powder, just a pinch. Okay, I'm going to mix that in. So right now I just have powder here. I just have starch and borax actually mixed together. A tablespoon of starch and just a little pinch of borax. It doesn't take much. Now it'd be nice to weigh that, but I really don't have equipment to do it precisely. So this is the best I can do, but it's okay. And now we need our glue. All right. And my recipe says 12 grams. Actually, it says a tablespoon, which turns out to be around 12 grams. We'll put in something like that here. I'm watching the scale. Oop. I maybe went a little over, but that's okay. You don't have to be super precise for this, but it's nice to have some idea what you're doing. You could do this with a tablespoon measure, but it's kind of messy that way. Okay, here we go. I'm gonna mix it up. Oops, gotta make sure you can see this. Of course, I'm doing this over my computer keyboard. That's probably not a great idea. All right, it's getting thick, it's getting sticky, it's getting messy. And at some point I'm gonna have to work this by hand. And I might need just a little more starch to do that. And I'm gonna have my ball. Whoa, there we go. Yeah. Okay, this is still pretty sticky, but the borax is starting to cross-link it. If I didn't put borax in here, and that would be the control, right? This would just be liquid, this would just flow. But because I put the borax in there, it's gonna get stiff. And that's pretty much my story. I'm gonna need just a little more starch to get this out of here, I think. But it is definitely getting stiffer. That's not quite a super ball yet. Great. All right, so I know it's about time to go, but you can do this. You can try this at home. And I had some super balls that I made earlier, so you can see what they look like, by the way. All right. This is what you should get. This one's a little hard now. Whoop. Okay, so that's where I worked in just a little more starch. How are we doing here? Still kind of liquid. I'm actually going to add another pinch of borax. Maybe I didn't get quite enough in there. Yeah, of course it would be good to weigh everything very precisely, but what I'm showing you here is that this is kind of like cooking. You know, you can just add a little bit more until it's right. Okay, and I'm going to need a little starch to actually work this, so that's there. I think what happened was I didn't get quite enough starch in there for the amount of glue that I ended up adding. So there it is. I think we're there now. Of course, I'm making a mess. You should really do this in the kitchen, which is where I did it last time. Okay, and that's it. Here we go. It's going to be a super ball. Yep. Whoa.
Were there any